Nuclear radiation. The nucleus of an atom consists of protons, which I'll show like this, and neutrons, which I'll show like this. The number of protons determines what element an atom is, and some elements exist with different numbers of neutrons in the nucleus. For example, carbon always has 6 protons. That is what makes it carbon. But in nature it can be found with 6, 7 or 8 neutrons. So here we have carbon with 1, 2, 3, 4, 5, 6 protons and 1, 2, 3, 4, 5, 6 neutrons. So it has 12 nucleons, making it carbon 12. Here we have carbon 13, again 6 protons, but now 1, 2, 3, 4, 5, 6, 7 neutrons, so 13 nucleons altogether. This is carbon 13. And again 6 protons, and now 2, 4, 6, 8 neutrons, giving 14 nucleons, so this is carbon 14. These are called isotopes of carbon. Isotopes have the same number of protons, but different numbers of neutrons. We can show the contents of the nucleus with this special notation, like this. The large letter here, sometimes we have a capital letter and a lowercase letter, is a symbol for the element. This number is the proton number, or atomic number. And this number is the nucleon number, or the mass number. For the isotopes of carbon, this would give the following. This is carbon 12 with 6 protons and 12 nucleons. Carbon 13 with 6 protons and 13 nucleons. And carbon 14, 6 protons and 14 nucleons. We can work out the number of neutrons by taking the number of protons away from the number of nucleons. If we specify a nucleus and its constituent parts in this way, it's what's called a nuclide. Some isotopes of some elements are unstable and will decay emitting radiation. One type of decay is called alpha decay. An alpha particle consists of 2 protons and 2 neutrons, making it a nucleus of helium. This is ejected from the nucleus. So this nucleus is going to lose 2 protons and 2 neutrons. Looking at the general equation for this decay, we have the parent X, which has got proton number Z and nucleon number A, becoming daughter Y. The proton number will drop by 2 because the alpha particle has 2 protons. The nucleon number drops by 4 because the alpha particle contains 4 nucleons. And we also have the alpha particle with 2 protons, 4 nucleons. Let's look at a real example of alpha decay. Uranium-238 undergoes alpha decay, so the atomic number or proton number drops by 2 to 90. The nucleon or mass number drops by 4 to 234. 90 protons makes it thorium, plus the alpha particle. You'll see that 90 plus 2 equals 92, and 234 plus 4 equals 238. So the atomic numbers and the mass numbers must balance on the left and right hand sides of the equation. Another type of decay is called beta minus decay. A beta minus particle is an electron. A neutron in the nucleus turns into a proton and ejects the beta minus particle. An electron antineutrino is also ejected. In this animation, this neutron with a black outline will turn into a proton and eject the beta minus particle. Looking at the general equation for beta minus decay, we have the parent X with proton number Z and nucleon number A becoming the daughter Y, and now the number of nucleons hasn't changed. a neutron has become a proton, so the nucleon number is unchanged. However, we've gained a proton, so the atomic number goes up by 1. To make the numbers balance, the beta particle has 0 nucleon number and -1 atomic number. This is the symbol for the electron antineutrino. Looking at a specific beta- decay, carbon-14 undergoes beta- decay, becoming number 7 atomic number, which is nitrogen. The mass number stays at 14. We of course have the beta- and the electron antineutrino. Now we'll look at beta+ decay. A beta+ particle is an anti-electron, which is antimatter. It's also known as a positron. In this case, a proton from the nucleus turns into a neutron, ejecting the beta+ particle. An electron neutrino is also ejected. In this case, this proton with the black outline will turn into a neutron, ejecting the beta+. Looking at the general equation for beta+ decay, we have the parent X with proton number Z and nucleon number A becoming daughter Y. The nucleon number doesn't change, as in beta- decay, but now we lose a proton as it becomes a neutron, so the proton number drops by 1. Now we have the beta+ particle with 0 nucleon number and +1 proton or atomic number, and this is the electron neutrino. Looking at a particular example of beta+ decay, here we have sodium-22, which undergoes beta+ decay to become neon-22. Finally, we have gamma radiation. This is high-energy electromagnetic radiation emitted from the nucleus. It has no charge, no mass, and no nucleon number, and so does not alter the makeup of the nucleus it leaves. Gamma radiation occurs when a nucleus is left in an excited or higher energy state after alpha or beta decay has taken place. As the nucleus drops to a lower energy state, the excess energy is released as a gamma-ray photon. Sometimes radioactive decays are displayed on a chart, something like this. In this case we have the number of protons on the x-axis and the number of neutrons on the y-axis. But do be careful, as exam questions will sometimes have similar tables but with different axes. Let's look at a particular decay. In this case, protactinium-234 becomes uranium-234 through beta- decay. Well, to work out where it goes on the chart, it has 91 protons, so it'll go somewhere on this line. We need to know the number of neutrons. 234 nucleons minus 91 that are protons means 143 that are neutrons. So 14391 is the place for 23491 protactinium. Now to plot the position of the uranium-234. Well, it will be on the 92 line now, and with one less neutron than the protactinium. So that will be down here. We can add a line coming from here to here to show the beta- decay. But uranium-234 is not stable, and it decays through alpha decay to be thorium-230. So, to position thorium on the chart, it will have 90 protons and it will have 140 neutrons. That is 230 minus 90. So thorium will be positioned here. We can now add a line joining these two, which shows the alpha decay. Do take care, as the chart might show atomic mass instead of number of neutrons. So here we have the proton number again on the x-axis and the nucleon number on the y-axis. Looking at the same decay as before, we have 234 protactinium, which would now be on the 91 protons, 234 nucleons line. It becomes 23492 uranium, which would now be here. That is due to beta minus decay. It then undergoes alpha decay to become 230 thorium. So in that case, the number of nucleons has dropped by 1, 2, 3, 4, the number of protons by 1, 2. So thorium should be positioned here. Let's just check. 230 nucleons is correct. 90 protons is correct. And that is through alpha decay. Naturally occurring radioactive nuclides with more protons than lead will follow a series of decays, eventually stopping at a stable isotope of lead. For example, here we have uranium-238, which undergoes alpha decay to become thorium-234. This in itself undergoes beta minus decay to become protactinium-234. Protactinium-234 undergoes beta minus decay to become uranium-234. This undergoes alpha decay, becoming thorium-230, which undergoes alpha decay again, becoming radium-226. This also undergoes alpha decay to become radon-222. Alpha decay again makes polonium-218. This carries on for several more decays, eventually becoming lead-206, which is stable. You won't be expected to remember decay series, but you may be expected to fill in a few gaps. You won't be expected to remember a decay series, but you might be expected to fill in a few gaps.